This example is really fun because it shows something really cool about math modeling with differential equations, and it also kind of illustrates how certain things can go wrong, and also illustrates stuff about bifurcations, and it's just good practice. So this is going to talk about essentially, renewable resources, right? If you have a renewable resource, it's really important that you don't harvest too much and then it doesn't renew anymore, okay? And what we're going to do is we're going to model this by looking at a population of fish. And we're going to use the logistic model to start. And again, this is going to show one of the powers of modeling. The logistic model says, right, we have some growth constant times the population. We have a carrying capacity, right? Logistic growth. We know this is, the number of fish. And here our independent variable is going to be season. So we're not going to be looking at days or years or whatever. It's per season, which I guess is kind of years. And then here, right, this is our growth constant. P is the population of fish. N is that carrying capacity. So lots of parameters. Capacity. Or at least two parameters. K and N. We're going to add a third parameter actually, because what we're going to be curious about is we're going to say, okay, well, what if we're fishing and we're fishing up C fish per year? This is one of the powers of modeling. If we're fishing C fish per year, how does that affect the model? Well, it's quite good, right? Or not good for the fish, but it's good for the power of mathematical modeling, is because we have this and we're losing C fish per year. Well, it's just going to be the exact same thing. We're just changing the derivative a little bit. The derivative will be exactly what it was before, but we're also losing C fish to fishing every year. And this is why modeling is so cool, why differential equations is so cool. This change is very hard to do to a solution. Like we know logistic growth model, we've solved that a million times, maybe not you and I, but it has been solved a million times. It's hard to modify though. But here, if we have a differential equation, a lot of times that's much easier to modify. And then something that a little fishy happens, no, there was a pun intended. Something a little fishy happens because this is no longer a separable differential equation. Or actually it is still separable. It's just a more complicated separable differential equation, I think. But anyway, so let's see how that changes things. And to do that, we're going to look at a graph of this right-hand side. So let's do that in the next page. All right, so if you look at a graph of the right-hand side, I should really use a thicker thing for my axes. All right, and we're going to graph, okay, let's say that this is going to be the y-axis, or the p-axis rather, sorry. P is our population. And we're going to look at how the population is changing, the derivative of p. All right, we're going to call that f of p. And specifically, what does this look like? Well, f of p is this, right? Remember, this whole thing is f of p. And specifically, let's not look at f of p. Let's look at f c of p. Let's look at the one parameter family. Now, again, there are three parameters in this differential equation. But we're just going to vary c. We're going to say, okay, if we look at some species of fish with some growth constant in some environment for that carrying capacity, let's just think about one specific situation, but vary the number of fishing. So we're only going to look at what happens as that changes. Well, then this looks a little messy, but all this is a parabola. And we've seen the parabola for c equals 0, right? C equals 0, we knew what this parabola looked like. When c equals 0, we had a 0 at 0 and a 0 at n, whatever n was. Right? This is just going to be n. And we knew this was a downward facing parabola. Who knows like how steep or whatever. But this is what happens if c equals 0. And furthermore, just like the last example, right, when we vary c, it's going to be a vertical translation. So if C grows, we're subtracting a bigger number. If C grows, we're shifting it down. And you can see, right? No pun intended. Gosh, too many puns. Right, if we shift it down a little bit, there's no qualitative shift. But if C grows enough, if the amount of fishing grows enough, right, we hit some breakpoint, right? What is this C we're curious about? Because that's going to be where it goes from 2 equilibria to 1 and then immediately to none, which is going to be very bad for the fish. How can we find this? Well, we just have to find out when there's only one real root, just like we started this whole section with. When is there one real root? We're going to have to do some manipulation. Okay, so let's copy this over. All right. Let's simplify this. If we distribute, this is Kp minus Kp squared over n minus c. And we're curious, when is this equal to 0? Well, what are we solving for? Right? We're solving for when this is equal to 0. Specifically, what value of c is going to make this equal to 0? And we need to do 2 things, right? It's not just when we find bifurcations, not just by finding when it's equal to 0, that's an equilibrium, but also when its derivative equals 0, right? This is a function of the population. So let's look at when its derivative equals 0 as well. Because again, going back to our graph, the derivative equaling 0 is important. That's going to be where that bifurcation value is, just like in the last example. So let's not worry about solving this just yet. We'll solve this after we solve this part. We'll take the derivative with respect to p. So with respect to p, this is just k minus 2kp over n. And we're also curious about when that's equal to 0. What are we solving for? All right. So we're trying to find the population that will help us find the bifurcation value. So here we're going to solve for p. What p makes this equal to 0? We'll add it to both sides, 2kp over n. You're going to find out the k's cancel. K doesn't really matter for this. And you're going to get that p is equal to n over 2, which makes sense. I keep going the wrong way, right? As this gets shifted down, it's the vertex that is this point. What's the vertex? It's n over 2. Things are symmetric. All right, so now that p is equal to n over 2, we're going to plug it in to find when f of p equals 0. Specifically, sorry, this should be f sub c. All right, now we're looking at what value of c makes the function value equal to 0 at this specific p naught. Right, we call it p naught. It's that equilibrium. So we evaluate this up here. We're going to get k times p, which is n over 2, minus k times p squared, which is n over 2 squared, over n minus c. And we want this to equal 0. So we simplify a little bit. We're going to get, wait, this first one should not be squared. That's a typo, right? Oh, it's not squared. I'm just writing too close. All right, this is just kn over 2. And one of the n's cancel, and we're going to get kn over 2. Oh, wait, I'm very nervous. No, it's, all right, great. It's k, the 2 gets squared. It's kn over 4 minus c. We want that to equal 0. Let's go off the page a little bit. Right, half of a kn minus a quarter of a kn. Only a quarter of a kn is left. And again, we could add c to both sides. We want this to equal 0. We're going to get that c is equal to kn over 4. We found our bifurcation value. It's a pair, right? Or how we find it is a pair. At this equilibrium point, we know the derivative is equal to 0. The derivative of this right-hand side, right, It's really quite a lot. So here's our bifurcation value. This is the value when very interesting things happen. All right. And again, you could go through and you could plot your bifurcation diagram. We're not going to spend the time here to do the bifurcation diagram right now. You are all capable of doing that. Got some good practice. But what we're going to get as our bifurcation diagram is something pretty interesting. It's going to be another sideways parabola. And again, I'm not going to be too precise here. When we make our bifurcation diagram, we're going to get something like this. And again, for the bifurcation diagram, we're going to be varying our parameter. We're going to be curious about how that varies the equilibria. And we know what the equilibria look like when C is equal to 0. When C is equal to 0, this is just a logistic model, right? We should be growing towards this carrying capacity of N. Right? If we have any population, we should be growing towards that carrying capacity N. But, and again, if we had negative population, to be decreasing, but negative population doesn't really make sense here. And what we're going to see is that as C is increasing, right? As C is increasing, what's happening to our phase line? Well, again, it's no qualitative difference. But now, this negative part makes sense. If you're fishing enough, then if there's fewer than some minimum required amount, the fish are going to die off. And again, if you're fishing quite a bit, then there's quite a few fishing populations that, again, if you're fishing too much more than there is fishing or fish out there, right? This is the value of P. If P is not very big, but you're fishing a lot, you're going to be going down to 0. And eventually, right, over here is that bifurcation value. What was it? Kn over 4. If you fish at Kn over 4, again, these are parameters, the carrying capacity times the growth constant divided by 4, then after that, what happens? It doesn't matter how many fish there are. If you're fishing that much, it's just going to die off. Okay? So knowing so this is like one of the applications for bifurcations. And again, I don't want a 30-minute video on this, so I'm skipping some steps here. But right, finding the bifurcation, which we know how to do, creating bifurcation diagrams, which we know how to do, and interpreting them is really important for understanding what's happening here, right? And showing that, okay, if you're fishing a medium amount, you have to be careful how many fish there are, or you could kill the population. And if you fish too much, it doesn't matter how many fish there are to start. You will kill them faster than they can reproduce. They will die off. And that's why it depends on that growth rate K, right? Because it really depends how much you can fish, depends on how much they're repopulating. All right, so that's pretty much all I wanted to say around here. Again, we talked about the bifurcation value. We talked about the meaning of the bifurcation value. And again, how this ties into sustainability. You have to be aware of this so that you actually can maintain your renewable resource. And it can stay a renewable resource instead of a used to be resource. That's pretty much it for this section. Bifurcations are pretty fun. Hope you enjoyed it and have a good rest of your day. Bye-bye. Please let me know if you have any questions.